Hello, hello, hello. Hi, I'm Chelsea Walton, and it is my great pleasure to introduce Dr. Mohamed Omar from Harvey Mudd College, who's going to give us a very, very exciting talk on the art and craft of problem design. Now, when he first told me that he was going to give a talk on this topic, I got really excited because I have borrowed a number of exam problems from him over time. I mean, he's really, really, really brilliant at crafting problems. So this is going to be a very, very good talk. Dr. Omar received his PhD from the University of California, Davis in 2011. He was a postdoctoral fellow at Caltech before joining Harvey Mudd as an assistant professor. Now an associate professor at Harvey Mudd, Dr. Omar has produced over 25 peer-reviewed research articles, one book now on sale at Amazon, and another book is in preparation. His work has appeared in prestigious academic journals, as well as in the popular magazines Scientific American and Forbes. He's done work in combinatorics, number theory, graph theory, and of course, pedagogy. In 2018, he won the Mathematical Association of America's Henry L. Alder Award, which, as many of you know, is one of the most prestigious undergraduate math teaching awards in the US. His mission is to, quote, change the world from math-phobic to math-loving, unquote. And in my opinion, he is the best one to accomplish this task. I mean, we're in for a treat. Thank you very much for coming, and let's welcome Dr. Mohamed Omar. Yeah.
All right, thanks so much for that warm introduction. So today I'd like to talk to you about the art and craft of problem design. So a lot of times in this profession, we talk quite a bit about the act of problem solving and the various facets of it, from dissecting a problem to its pieces, to all the parts that go into solving a particular problem. But we don't talk a lot about the following question. How does one make a problem that's not just good, but that's great? And this comes up in a lot of facets of our careers, and particularly the facets that I work in by far the most. Whether it be problems in teaching, like assignments or exam problems, problems that come up in academic research, or problems in one hobby that I like a lot, which is creating math contest problems. This is a central focus of a lot of these different moving parts of my career. And so today I'd like to talk to you about this in these different spheres. And I want to use this mantra, which is going to be a part of the whole talk, and the mantra is vamos. Taking values and matching them with math-oriented skills. I'm going to talk about the matching of these two and how you can use these to create amazing problems in teaching, mathematical contests, and research. I want to start by talking about using the vamos mantra in teaching, particularly looking at a few values that appear time and time again in teaching practice. The importance of rigor, ease of grading, looking at problems from multiple perspectives, and then thinking about how to get students to engage in the problem-solving creation process using this vamos mantra. All right, so I'm going to start off with a concrete problem to get us right into the action. The problem of having the value of needing rigor in a calculus problem. So imagine you're in the following situation. You're teaching a calculus class, single variable calculus. You're at the end of the semester and you're creating an exam review. And you want to create a problem whose goal, the value you're trying to instill, is the actual need for rigor in calculus. So you have a problem where the math skills are derivatives and limits. And here's a prototypical example of such a problem. Use the limit definition of the derivative to find f prime of 0, where f of x is x times the sine of x. Okay, I claim this problem here is actually not good for matching the value that we want with this problem. Why? Well, at the end of a calculus course, students know how to approach this problem without needing the rigor. They can use the product rule. You have two differentiable functions. and then plug in x equals 0 to get the answer. Right? So if we really want to instill the value of needing the rigor of calculus, we should change this problem slightly so that at least one of the functions involved is not differentiable, and so the product rule won't apply. We can do that by, say, changing sine of x to the absolute value of x. Now we have a function that's continuous at 0, the absolute value of x, but is not differentiable. So an attempt to use the product rule, though I promise you, you will see attempts to use the product rule, right, won't work in this setting. Let's see how this plays out by using the limit definition of the derivative to show this thing is actually differentiable at 0. Okay, so we have something like this. F prime of 0 is the limit as h approaches 0 of this difference quotient, which simplifies to h times the absolute value of h divided by h. And we're left with the limit as h approaches 0 of the absolute value of h. And this is 0. Okay, great. So we've augmented the problem to something that really actually requires the rigor that we're trying to set as a value. But we can take this further using or looking at the math value that we have, which is this rigor, and the skill we're trying to instill, which is using derivatives and limits, to observe what's really going on here in the bolded statement. So in bold, we have the limit as h approaches 0 of the absolute value of h. And really, all that was required to go to that next step is the fact that the absolute value function is continuous at 0. So we could have replaced the absolute value by any arbitrary function that's continuous at 0 and get a similar type of answer. So we can do that to make this problem not just good, but great. Replacing absolute value of x by any arbitrary continuous function. Let g of x be any continuous function. We use the limit definition of the derivative to find f prime of 0, where f is g times the function x. And so now we have a problem that not only instills the value of rigor once, but it does it twice. If we look at the actual solution, we have the same setup. F prime of 0 is the limit of this difference quotient. And the second last line we have is the limit as h approaches 0 of g of h. And so we've afforded our students another opportunity to use the fact that g is continuous to establish that the derivative of f at 0 is g at 0. And a nice piece of this is that g can be any continuous function you like. So you can augment this by asking students to create interesting continuous functions that look kind of wild, that all of a sudden by multiplying by x become differentiable. So this is a prototypical type of thing that I like to do. Start with something that seems reasonable and then really look at the value that I'm trying to instill to augment the problem to something that works in the favor of really instilling that value. So let's look at another example of something like this. And this is ease of grading. So the value I want to instill here is making a problem that's easy to grade. Now you might think this is not a very virtuous value, right? But it's one that definitely is very pragmatic, right? If you're grading a stack of papers, it would be nice to create a problem that just has simple and easy numbers, things that are easy to work with, not too complicated. And to make this slightly challenging, what I'm going to do is pair it with a math skill that makes the ease of grading somewhat difficult, but still in the same realm of calculus. What I'm going to do is look at a problem of sketching a curve. So the reason why this gets complicated when you're looking at making a problem that's easy to grade is that curve sketching has a lot of facets to it. So you might want a problem that has, say, a local minimum and a local maximum and maybe an inflection point at some place. These are three different things that involve various derivatives of a function. How do we achieve this while making a problem that's easy to grade? All right, so if we want local minima, local maxima, and an inflection point, and something that's manageable, maybe we'll try to work with just a polynomial. You know, if we had a rational function, things get messy. We know where that goes with students in general. Stick with a polynomial, see what happens. Now, a quadratic polynomial won't work. Quadratic polynomials, when you graph them, either have just a local minimum or just a local maximum. So we'll go to cubic ones and see what we can do. If you have a cubic polynomial, when you differentiate it twice, you'll get something that's linear. So you get an inflection point. And so what we're going to do is try to craft a problem where all of the critical points and the inflection points are small integer numbers, right? And that'll make everything sort of more manageable for us to grade. So I'm going to start off with a function that looks like this. And you might ask, why this function? X times the quantity x minus a squared. Well, first of all, you notice if I select a cleverly chosen value for a, like an integer, then this thing will have integer roots that are not complicated for a student to find. Moreover, you might notice something about differentiating this function. If you differentiate it using the product rule, each summand will still have x minus a as a factor. So the derivative will have x minus a as a factor, and so I already know that a is going to be a critical point of this function. Right? So if I choose a cleverly, like some small integer, I already have control of one of the critical points. This is a cubic polynomial, so its derivative is quadratic. I know one of the roots is a. There's another one, so when I actually differentiate this and look to see what's happening, I can try to pick the value of a cleverly so that the other root of the derivative is also manageable to deal with. So let's look at how this plays out in this particular example. So here's f of x. I've differentiated it using the product rule. And then I factor that because we have a common factor of x minus a. And if you put things together, you get x minus a times the quantity 3x minus a. And so one thing I could do is select a so that it's a multiple of 3. If I do that, then the factor 3x minus a will have an integer root. And this will be something that's manageable to deal with when looking at student answers. Now, luckily, if I look at the second derivative, it's 6x minus 4a. If we did choose a to be a multiple of 3, 4a would be a multiple of 12, and we'd also get an integer root for the second derivative as well, which makes things manageable. Now, again, we want this to be easy to grade. So if you pick a to be 333, that's not a good choice for a multiple of 3, right? Why not make things simple? Why don't we just make a 3, right? If we do that, we'll have 3 and 1 as a root of the derivative, and then the second derivative will have 2 as a root. And so we have nice small integer values to work with for our critical points and inflection points. In this case, it turns out you'll have a local min at 3, a local max at 1. You have these integer roots 0 and 3, and an inflection point at x equals 2. Right, so everything is sort of in a compact region, manageable for sketching the curve, and the numbers are not too wily, so grading won't be too complicated, hopefully. So this is interesting. Actually using mathematics itself to construct a problem that's easy to grade, right? All based on this Vamos mantra of looking at what it is that you have as a value in order to create the problem at hand. All right, so we've established that with ease of grading. I want to go on to one more problem that's a little bit more involved and still in the realm of calculus, and that has to do with the value of thinking about problems from multiple perspectives, right? So how do we, if we have the value of creating a problem with multiple solutions that have fundamentally different approaches, how do we do that in a situation where, like in this example, we'll want to instill the math-oriented skill of classifying critical points in multivariable calculus? Now, for some of us, we might think, not this stuff. It's quite involved, but I'll go through the process of just taking a problem and looking at how to classify local minima to remind ourselves of how this multivariable stuff works, and then thinking about how to augment that problem to give students the opportunity to look at things from multiple perspectives. Okay, so here's a problem I'm going to look at. Find all local minima of the function f of x equal to x cubed minus 3xy plus y cubed. So let's start with the standard approach on how to figure out the local minima to a function like this. So you start by taking the gradient, whose components are the partial derivatives of the original function with respect to x and then with respect to y. So you get 3x squared minus y and 3y squared minus x. The critical points are achieved by setting these two things equal to 0. So you have something like x squared minus y is 0 and y squared minus x is 0. If you were to figure out the zeros of these polynomials, you'll get that the critical points are 0, 0, and 1, 1. Okay, so this is sort of the standard multivariable thing to do. And then you need to do a second derivative test. I'm not going to get into the details of that, to figure out which points are local min, local maxes, or saddle points. And here it turns out that 1, 1 is the only local minimum. All right, so standard approach to a standard type of multivariable problem. How do we change this problem to something that can give us insight on multiple perspectives in a multivariable setting that also maybe illuminates something about the geometry of what's going on? So I want to make an observation about this. Here's an actual graph of the function, and thinking about it as z equals f of xy. And it kind of looks like an eagle or a hawk trying to attack you. But anyways, so this is drawn from the following perspective. You notice there's these three axes. The bottom two are x and y. And so we're standing looking sort of like the plane x equals y is standing right here, right? So the line, the plane x equals y is sort of right here, and these axes x and y are coming out of the center. So there's a symmetry you notice in the graph about the plane x equals y. We can actually see that in the function itself. If you interchange the role of x and y in f of xy, you get the same function back. Okay, how can we exploit this? Well, say you have a point AB and you look at the image on the actual surface. Whatever is happening locally in the geometry at that point is the same thing as what's happening when you look at the image of BA. And the reason is because we have symmetry about the plane x equals y. So if you additionally furnish this problem with the information to the student that there happens to be a unique local minimum, then that unique local minimum has to happen at a point whose coordinates are both the same. Right? Because if it didn't, if we had a point AB where A and B were different and it was a local minimum, then BA would also be a local minimum as well. Why is that helpful? Well, if we go ahead and change the problem to the statement, hey, here's a function, it happens to have a unique local minimum, find it, we know by this geometric argument that the local minimum happens at a point of the form AA. So we can restrict our search for this local minimum to points of this form. Right? What does that amount to? It amounts to taking our surface, which is the surface z equals f of xy, and cutting it with the plane x equals y, and looking only at the points of intersection to find out where the local minimum is. But that is a one-dimensional curve, and so we've transformed our problem that happens in 3 dimensions to a graph in one variable. Right? It's kind of a remarkable thing that comes from this geometric insight and the symmetry that's happening in the function f. So let's do that explicitly. Here's our function f. We know that our local minimum has to be a point of the form AA. So we'll make this function g of x, which is f of xx. This is a one-variable function, and we can use this to search for our local min. Right? If we look for, now the point is, if we want to find a point in our picture upstairs that is a local min, it has to be a local min in the restricted picture, or its projection, because the surface is a much larger piece and this restricted curve lies on the actual surface. So we can do calculus in one variable. We'll do that here. In this one variable, we have 0 and 1 being the points where we have critical points. And if you test the second derivative with 0, you'll get that it's actually a local max. So the only local min in the one variable function happens when x equals 1. And so that's the only possible candidate for this, being related to this unique critical point in the three-dimensional case. So our local min is 1, 1. Okay, so an interesting problem with this different insight, and I want to mention something about this problem. This is not an easy perspective to come up with at all, right? So a suggestion for something like this would be to make it a multi-step problem where you say, hey, there's a traditional way to solve these problems, but now let's realize that we're really working with things that are geometric. So let's look at the picture and then look at the consequent algebra to see what's happening. Great, so these three problems sort of illuminate a little bit about the types of ways that I see mathematical problems in these realms that are quite different than what's typical. If you want to see a lot more things like this, I actually have a YouTube channel that has a lot of interesting mathematical insights with videos that demonstrate problems just like these. So feel free to take out your phone and go to YouTube, and it's YouTube and my name and math, so it's nothing complicated. And you can I post videos about twice a week with stuff like this. Okay, so let's move on to another facet. We've talked about how to introduce or think about the Vamos mantra in teaching, but let's think about it with respect to students. So I hear often professors creating or asking students to create problems for midterms themselves, right? So the value here is completely student-made. You have your students in your class and you ask them to come up with a problem that might be prototypical for a midterm or a final exam. So I did this with an optimization class that I taught several years ago at Harvey Mudd. And maybe a first attempt at a problem like this, which I hear quite often, is construct a great problem for a midterm. Okay. If you do that, you don't have any sense of what the students value, right? What is it that they're trying to actually demonstrate in the problem that they're creating? So you might make a second attempt and say, let me ask students to construct a problem they deem easy and a problem that they deem hard. Okay, this is a great second attempt because there at least is some idea of some value introduced. However, you're asking them to demonstrate things at extremes. So you don't have a sense of what the sort of relativity is, and that gives you a much stronger sense of where their values are really kicking in. And so in this linear optimization class, I asked a problem on an assignment just before the midterm that looked much more like this. Give an example of a midterm exam problem that you would rate as a 2 out of 5 in difficulty. Provide a solution and explain why you would rate it a 2 out of 5. So you see, this actually takes some thought now, because your problem can't be too easy, but you have to explain why you don't think it's too easy, but it's still easier than moderate, right? And then there's the polar opposite of this. Give an example of a problem that you would rate as a 4 out of 5. And I could see a lot of the different value systems that were occurring in this course. This is an optimization class, so there are like computational facets and theoretical facets as well. And I noticed that some people rated difficulty on sort of the computational axes and some on the theoretical axes, and that was interesting to see. But it was much more illuminated by having this 2-4 split rather than the extremes that I mentioned before. Okay, great. So let's move on to this other part of my personal career and how the Vamos mantra has really played into it, and that's in mathematical contests. So I've worked a lot with mathematical contests over my career at the high school level, and from multiple choice contests to contests that have full answers. And a question that I get asked all the time is, how do you actually create a math contest question, right? Usually sometimes they involve some trickery and some different insight. So I'm gonna show you how I use the Vamos mantra to actually create one. And I'm going to create a problem that instills 3 values at the same time. Novelty, it's a multi-step problem, and one that merges different ideas from different areas of mathematics. Okay, so the problem, which is going to instill these three values simultaneously, is the problem of solving a polynomial equation. Now, it doesn't make sense to start with a quadratic equation because there's a sort of a typical way to solve quadratic equations by either factoring or using the quadratic formula. So I'm going to start with a cubic equation. So here's a first attempt. I write down a cubic equation, solve it. Okay, so novelty's out the window, but maybe there's multi-step and merging ideas. Not really any merging ideas from different areas of mathematics, but maybe there is something that's multi-step here. For example, you have to make an observation like if you plug in 1 for y, you get 0. Yeah, right? 1, yes. 1, 0. Right? So 1 is a root of the polynomial on the left. That means y minus 1 is a factor of the polynomial on the left. I can factor y minus 1 out and get a quadratic left and use that to solve this equation. Okay, so let's make a second attempt at this because it's missing novelty and merging ideas from different areas of mathematics. And here's what the second attempt's going to look like. At first it's going to look like, where did this come from? But I'll explain sort of in a second where it did. So the problem looks like this. In a geometric sequence, the sum of the fourth term and twice the first term is the same as 3 times the third term. Determine the common ratio. Okay, that looks really different than before, but I actually claim it's not that different. So let's think about the process. So what are these words that I'm using? So we have like the fourth term of something and a first term and a third term, and they're forming a geometric sequence. So I might as well write down the first 4 terms. So a geometric sequence is one in which any term is a constant multiple of the previous term. So if the first term was like a, then the second term is ar, where r is some constant. The next term is ar squared, and the next term is ar cubed. Okay, so here's where this problem came from in my mind. If you look at these 4 terms, and you created a linear equation in them, so multiply them by constants, add them up and set it to 0, then you'd have an equation that has an a factor everywhere that you can eliminate, and you're left with a cubic equation in R. Okay, so I've introduced a completely different mathematical area that leads to a problem involving a cubic equation, which was the goal to begin with. All right, so let's actually do this in this process. So the fourth term is ar cubed, and then we're adding 2a to get 3 times the third term, which is ar squared. If we factor the a out and rearrange, we actually get exactly the same cubic equation that we had in our original example. Okay, great. So this is definitely a multi-step problem. There are definitely merging ideas of different areas of mathematics. But I claim this is actually not that novel. So one of the things is, again, I have a history of working with math contests, and a big part of math, one thing I've seen a lot of math contests is this idea of taking geometric sequences and doing something funny with them and then having a problem. So something that happens a lot. Also, this kind of feels very fabricated, right? It's like I just introduced, look, what is this whole thing about twice the fourth term, and it seems like something I made up out of the sky. So here's the last attempt that actually turned out to be the problem that I submitted to a contest and that was used. I'm going to take you through this and give you an idea of where it came from the first and second attempts. So the third attempt is the following. A sequence whose first term is positive is constructed so that any given term is the perimeter of a square whose area is the preceding term. Okay. If the first 3 terms form an arithmetic progression, determine all possible values of the third term. There's a lot going on with the words in this, so we'll take it step by step and see what's going on. Okay, the first thing I do, you have a problem, there's 3 terms involved here, I don't know what they are, so I'm gonna make the first term x, because I don't know what it is. Okay, Now, what the statement here says is that any given term is the perimeter of a square whose area is the preceding term. So we're going to deem the first term to be the area of something, right? And the second term is going to be the perimeter of that something, that square. So the second term is the perimeter of a square. That's 4 times the side length. The side length of this square, well, it's the square coming from the first term. The first term is the area of that square. So its side length is the square root of the first term. And so the second term is 4 times the square root of x. Okay. In fact, this is the relationship between any 2 successive terms in the sequence. Any term is going to be 4 times the square root of the previous term because of that first sentence in the problem statement. So the third term is going to be 4 times the square root of the previous term, which simplifies to 8 times the 4th root of x. Now, the information that we're given here is that the 3 terms form an arithmetic progression. So there are numbers like 10, 6, 2, or 5, 3, 1. There's a common difference between the successive terms. That means that the first term minus the second term is the same as the second term minus the third. And so we end up with the equation that looks like this. X minus 4 root x is 4 root x minus 8 times the 4th root of x. This looks like a mess. Let's make this a little bit simpler. Let's substitute y for the 4th root of x. If we do that, then the root of x is going to be y squared, and x is going to be y to the 4th. And now we have a 4th degree equation in y, but there's a factor of y all throughout. If we rearrange this, factor the y out, we get y times a cubic equation. That cubic equation happens to be okay to work with. If you plug in y equals 2, I think you get 0. So if 2 cubed is 8 minus 8 times 2 plus 8, yeah, 0. So y minus 2 is a factor, so that works out to be okay. But at this point, you might be asking yourself the question, where in the world did I come up with this idea? Right? It seems like a much bigger leap from the first attempt to the second attempt compared to this attempt that I have here. Well, here's the idea. So I know the following. If you have a square, perimeter is linear in the side length, and area is quadratic in the side length. So this third term, if I deem it to be y, whatever it is the perimeter of a square, right? And so the second term is going to be a quadratic in y, right? It's going to be something like y, something times y squared. And similarly, the first term is going to be the square of that. So it's going to be on the order of y to the 4th. So these 3 terms I knew would be y squared, and y to the 4th in order of magnitude. And so if I had a linear equation involving them, I knew there'd be y as a factor, and the remaining thing would be a cubic, right? And that's exactly where all this is coming from. Cool. So the Vamos mantra in action, to give you an idea of how I create contest problems with particular values in mind, implemented with the math-oriented skills that I want to demonstrate. Great. So finally, I'm going to recap first, actually. So we went from our first attempt, which is a multi-step thing, kind of multi-step. Then we made a second attempt that merged ideas, but it wasn't novel enough. The third attempt is where we really got some novelty in. So really, using the Vamos mantra, I find is an iterative process where you have many attempts that get you to the goal that you want. Okay, so finally, I want to talk about how Vamos plays a role in research. Research is a big part of my career. So how do we look at the values that we have or want together with linking with math-oriented skills that we have to come up with good, great problems in mathematical research? And luckily, I can use some ideas that have already been shared with the world by experts in research, a particular expert, which is the person who introduced me in the talk, Professor Chelsea Walton from UIUC. And she shared a really great idea of a set of values that one should instill when thinking about how to create not just a good, but a great research problem. And I sort of adapted it to what I've thought about as well. So think about three things: want, can, and should. Right? Want is picking a problem that is of deep interest to you, so that no matter what happens, when you're working on a research problem, you're bound to reach some obstacles and stagnant points. You still want to push through. Can, which means will you be able to actually get somewhere on this problem? And a good way to test, to figure that out is to pick problems that really build on your years of expertise in the mathematical field that you study. And should, is there actual community interest in what it is that you're doing? Is this work that will link to work that others have done? And is this work that others will use in the future and build upon? So I'm going to talk about this in the context of one particular family of problems that I've thought about over the past few years, which have to do with convex sets and their intersections. So I'm going to briefly introduce what a convex set is. A convex set in Euclidean space is a set in which any 2 points can see each other. Right, so you have a point x and y, and you should be able to see x from y inside of the set. In other words, for any 2 points in the set, the line segment between them lies inside of the set as well. So on the left, we have an example of a convex set, whereas on the right, we have an example of a set that's not convex. Look at these 2 points x and y. Unfortunately, they can't see each other through the set, not because of dim lighting, but because there's an obstacle. Okay, so what have I been thinking about with convex sets? I've been thinking a lot about their intersection. So on the left, you have 5 convex sets that intersect, and you see it dissects space into all of these regions. I've highlighted one of these regions in blue, and this region lies inside of the 3rd convex set and the 5th one, right, but doesn't lie inside of any of the others. I've marked that with a binary string that I call a code word. That's 00101. It has a 1 in the 3rd and the 5th bits, and zeros everywhere else. Right, so I can make a table that records all of the intersection data of these convex sets on the right-hand side. So for example, that blue region is recorded by that blue binary string on the right-hand side. And here's a list of all of the intersections. You notice, for example, on the right-hand side, you don't see 1, 1, 1, 1, 1 anywhere, because not all 5 of these sets intersect. Okay, so if you have a picture like the thing on the left with a bunch of convex sets and how they intersect, you can write down the list on the right. The fundamental question in an area of research that I've been working on for quite a while now is, can you do the reverse? If you imagine writing down a bunch of binary strings on the right, and you ask the question, think about this as a list of demands, right? Somebody from up high says, hey, here are a bunch of intersection patterns I demand of you for your convex sets. Can you create them on the right-hand side? Well, can you? That's the question, right? What obstructions are there? What restrictions are there? What techniques can you use to determine whether or not it's even possible? Can you do it in different dimensions? Are you restricted to only doing it in 3 dimensions instead of others? So a lot of work has been done on this. So the way I want to word this research problem is to ask the question, when is a code is the list on the right-hand side, a convex code, meaning it can be achieved as the intersection pattern of a bunch of convex sets like we have on the left. All right, so lots of work has been done on this. And a lot of the work has focused on 2 things. One is determining what obstructions there are to doing this. And another is understanding families of codes that you know for sure for which this can be done. Another thing that has been of interest is the dimension question. Maybe some of these things can be done in dimension 2, but not dimension 1. Dimension 3, but not dimension 1. A few papers are listed right over here. And so the question I want to ask is, what can I contribute with my background to this field thinking in terms of this VAMOS mantra. Well, one thing that I've studied a lot in mathematics is combinatorics. I like to count. So one of the things I notice in this field is that there aren't a lot of questions about how many convex codes there are. If you're given n convex sets, how many are there? So maybe this is a great way to proceed, thinking about the want, can, and should paradigms of my value system in this particular setting. All right, so I have a deeper interest in counting, that's already there. It builds on an expertise. I've had years of experience with combinatorics, and a lot of people who work in this field work more on the geometric side and algebraic side of things rather than the combinatorial. And I think there'll be a lot of community interest because there'll be new methods given my combinatorial skills that I have from my background, together with synthesizing the combinatorial aspects with all of these geometric and topological findings that have been done in the past. Okay, so how do we build an actual problem from that? Some of the enumerative questions of how do you count the number of codes have actually been addressed, at least in dimension 1 in this paper here by these two individuals. But we can beef this up a little bit and ask how many convex codes are there on n bits period, make that a function f of n, and maybe stratify that function based on dimension to be fnd, the number of realizable codes in d dimensions. At this point, I have to sympathize with you. You just got introduced to this whole concept, and you might be like, okay, I'm not keeping track of what's going on, right? But that's not the point. I think the point of all of this is not the mathematics is happening, but the question of how am I actually building questions here? The focus in this research area so far has been all about questions of constructing examples, finding obstructions, or understanding restrictions on dimensions. Questions of counting have not been at the forefront, and counting is an expertise that I have. So using this VAMOS mantra, my values, together with my mathematically oriented skill being combinatorics, I can build these two counting functions and explore them together with all of the research that's been done. Right, so here's a list of some particular things that have been discovered in previous research that run the gamut from algebraic obstructions to topological restrictions to understanding codes that we know are realizable. And then on the right, sort of aspects of the function that I created, together with the actual combinatorial expertise I'd match it to address and match with these different findings in these different areas of previous research. So a great example of using the VAMOS mantra together with the help of the ideas from Professor Chelsea Walton in order to create a problem that's not just good, but really great for research. Okay, so now we've talked about the VAMOS mantra and how it plays out in research and teaching and contests, which are a particular interest of mine. But one thing that I want to share with you that is really at the heart of what I've built my career on is where all of these things meet. That's when things get really beautiful. And that's when I think the VAMOS mantra really, really shines. And in particular, I want to share just briefly with you how a lot of the values that I have in teaching in contests have been influenced by things in research and vice versa. So just a couple of examples. I'll send your attention to the picture on the bottom right here. Here you have a triangle and a parallelogram, and then you have this, I think it's a heptagon, maybe a hexagon at the bottom, that looks like it's obtained by taking the triangle and sort of sliding it across the parallelogram, right? So this process is called a Minkowski sum, and for those who study geometric combinatorics, it's something that's sort of a staple in the field. Okay, if you change this to being a triangle and a square, you get an interesting object that's manageable to deal with. And I want to share with you that one value in mathematical contests is really hard to achieve is finding problems that are relatively easy to work with, but that are actually novel. So having a problem that's like, so-and-so has a cup and it gets cut in a third. I don't know why you're cutting a cup. But anyways, it gets cut into the third and then you add a fourth. What's the result? That's not a really original problem. So one of the things that I did is I took this area of expertise that I have, the geometric combinatorics, took the simple idea of taking a triangle and a square, asking for the area of the Minkowski sum. When I submitted this problem, it was deemed as this completely novel thing, right? But for anybody who studies this area, it's not novel at all. It's this transference that allowed me to achieve the value that was wanted in the contest setting by something that I've done and worked with in the research setting. This is something that I've also done in contests on the other end of the spectrum. It's really difficult to find problems on mathematical contests or create problems that are novel and actually difficult. And one way that I do that with research is thinking of taking examples from my research papers that come from maybe lemmas and asking for proofs of such principles in a problem that can be stated independent of the research itself. Now that works in some research that I do. In some research I can't do that at the high school level, but it's been something that's been really fruitful in that setting. Okay, another example is thinking about the value system I have in research and instilling that into teaching. So when I think about the process of actually doing research, a lot of it is muddling around with ideas that I don't even know how to articulate based on experience that I have, and then eventually building an idea that I can communicate concretely to people. However, somehow that's not the way we tend to teach, right? Even in inquiry-based learning, there's still sort of this like paradigm where we're working with something very concrete. We're not in a muddy state where we don't know anything that's really going on. And so I created a book, Number Theory Toward RSA Cryptography, where the chapters read exactly like this idea. You start with, what is a prime number? Okay, when you were young, you learned kind of what a prime number is, but what is it really? And then how do you talk about it? And then how do you change from a colloquial language to an actual concrete, formal mathematical language, right? And each of the chapters in this book does exactly that. Okay, so back to our original question then, right? The question is, how does one make not a good, but a great mathematical problem in the various settings that come up in our mathematical lives? And for me, in teaching and research and the contest work that I've done, the answer really lies in this VAMOS mantra. Taking your values and matching them with the math-oriented skills that you want to achieve together can take you from building problems that are not only just good, but are really fantastic and achieve the goals that you really want. So thank you for your time.
Wow, that was really excellent. I think we are at the limit. Wow. For questions, maybe we can take like 2 questions at the mics here, one in here and here. Are there any questions? If not, we could talk afterwards. Okay, let's talk afterwards. Let's think, Professor, one. Yeah. Yeah.
Good. So great talk. I guess one question is, how do you have well-defined values, right? So I imagine one problem in the VAMOS approach is having an ill-defined value, right? And that can get in the way and muddy up your process, right? So are there techniques or strategies for having a well-defined value?
That's a great question. So the question is, how do you actually go through the process of having very well-defined values in the first place before implementing them together with a math-oriented skill? So typically, I think about sort of the end result that I want from what I'm trying to achieve. So let me give, well, I can't really go back in the slides, but let me think about the value of having a a multiple perspective problem, right? So that's kind of a very vague problem to begin with. But really what I wanted in the specific setting that I had was I was working with a multivariable calculus problem. And one of the things I often notice in multivariable calculus classes is we talk quite a bit about the mathematics that's going, the calculations that are going on, but not how they match with the geometric intuition that's happening. So to make this actually more concrete, I can say what I want from the multiple perspectives is a perspective that illuminates what's happening algebraically and one that illuminates what's happening geometrically and showing how those two relate. And now I have something concrete that I can use to actually build the mathematical problem. So I think the transference from your value to actually mathematically stated ideas that are not concrete yet is the bridge between the two. Yeah.
Well, I think that we're out of time. Let's thank Dr. Omar once more.